Hi, my name is Tim Eibel. This is a series of structure-related videos which you're about to see, and I really hope you enjoy them.
Let's now start thinking about beams. In many ways they're similar to trusses, and we can analyse them in similar ways by looking at using a free body diagram. So we start with a simply supported beam like this, with a load in the middle, and of course we can easily find the reactions. They're simply P upon 2 on the left-hand support and the right-hand support, both acting upwards. But how is the load P carried to these supports? What does the beam feel between the load and the supports? So to answer this, we're going to take a cut. We're going to take a cut to start with on the left-hand side of this beam, and we're going to analyse that free body diagram which exists. So we start by taking this cut, and we'll call it a length x. Remember that we're taking a cut on the left-hand side, so x is less than half of the length of the beam. So we start by drawing in the reaction on the left-hand side. And in order for that free body diagram to be in equilibrium, clearly there must be a downward force, which is also valued P upon 2 acting at the cut. So we draw that in. That free body diagram is now in vertical equilibrium, and that downward P upon 2 force at the cut is called the shear force at that cut, and it must exist in order for that free body diagram to be in equilibrium. But look carefully now at that free body. It's going to spin. It's going to spin in a clockwise direction, and therefore we know that at the cut there must be a moment acting which will, as it were, spin that free body back in an anti-clockwise direction. So we'll call that moment M, and in fact that is a bending moment at that cut. That is the moment, the internal moment, which must exist at that cut to maintain equilibrium. So what's its value? Well, what we'll do is we'll take moments about the cut. So if we take moments about the cut, the shear force P upon 2 passes through the cut and is ignored in the equation, and we see quite simply that the bending moment at that point, at the cut, must equal P upon 2 multiplied by the distance x to the reaction force. Look carefully. The value P upon 2 for the shear force is a constant regardless of where I've made the cut x in the left-hand side of the beam. And look carefully at the bending moment. The bending moment varies linearly with the value of x. What if we decide that we would like to cut the beam on the right-hand side? So if we cut the beam on the right-hand side, what we'd find is that in order for us to have equilibrium of the free body diagram now, the shear force at the cut would have to be P upon 2 again in order to have vertical equilibrium, but this time it would be acting upwards, and that free body is now in vertical equilibrium. And again, this free body would rotate were it not for the bending moment M, which exists at the cut. And in this case, the bending moment is slightly more complicated than before. It's still fairly easy. We just have two loads to worry about, two distances, and we can calculate what the bending moment is at the cut. Right, let's look at the shear forces a little more closely now. To start with, it's a good idea at this point to introduce a sign convention. So that's what we're going to do. We're going to choose any shear force which has a downward shear force on the left-hand side of a piece of the beam and an upward shear force on the right-hand side of the beam. We're going to say that's positive. And conversely, if we have a shear force system where we have a shear force which is up on the left-hand side and down on the right-hand side, we're going to call that a negative shear force. And you'll see why we make this, why we introduce this sign convention in a second. We're now in a position where we can draw exactly how the shear force and the bending moment vary along the beam. And that's very useful to us because it gives us an instant visualization of what's happening across the beam, whether we're interested in shear forces or bending moments. So let's start doing that. We know from what we've just discovered that on the left-hand side of the beam we have a negative shear force of value P upon 2. And on the right-hand side of the beam we have a positive shear force of value p upon 2 as well. So we can sketch that in. The convention is to draw negative below the line and positive above the line. For the bending moment diagram, in other words how the bending moment varies across the entire structure, convention is to draw a positive bending moment on the tension side of any structure. So let's do that. We know that at the support on the left-hand side, the bending moment must be 0. Clearly, to the left of the beam, we have fresh air. We must have 0 bending moment at a simple support. The same goes for the right-hand support. So how does the bending moment vary? Well, we know from above that the bending moment varies linearly, starting at 0, and it has a value of p upon 2 multiplied by x as x increases towards the center span. Then, on the right-hand side of the beam, it varies according to what we've discovered as well, which is linear, a linear variation, and that goes back to 0 on the right-hand, at the right-hand support. So we can sketch that in, and what we find is that we have a bending moment diagram which has a maximum in the middle, and that value is PL upon 4. We can apply exactly the same principles now to a simply supported beam under a uniformly distributed load. What we do is very similar to before. Take a cut a distance x away from the left-hand support, and this can be any distance x. We no longer need to worry whether it's before to the left of the central load or to the right of the central load. We can take a cut at any distance x. What we can now do is we can draw in the required shear force and the required bending moment diagram, the required bending moment, which must exist at the cut in order for this free body to be in equilibrium. So let's look first at the equilibrium. The shear force at the cut, if we assume that it acts downwards, if it is acting downwards, it must equal everything acting up the page. And everything acting up the page will be W L upon 2 minus W times X. The bending moment of the cut is easily found by taking moments about the cut. It's presumed to start with that it is acting in an anti-clockwise direction. This makes good sense because we know that we will end up with tension at the bottom of the beam, just purely physically looking at the beam to start with. It's loaded from above, we must have tension at the bottom, and therefore the bending moment at that cut must be the support reaction, WL upon 2, multiplied by the distance x, and then minus WX times x upon 2. X upon 2 is the distance from the cut to the center of the spread load W. What this means is that clearly now we have a shear force which varies linearly across the beam, and we have a bending moment which varies parabolically across the beam. So as before, we can now draw the shear force diagram and the bending moment diagram for this load, for this beam, which is a uniformly distributed load all the way along it. Now we know that the shear force will vary linearly, and if you look carefully, we know that the shear force has a value of WL upon 2 minus WX. If x is 0, in other words at the left side of the beam, the shear force will act down with a value of WL upon 2. That means it's a negative shear force of value WL upon 2. And if x is L, then the shear force will act up on the right hand side, and therefore we'll have a value of WL upon 2 on the right hand end of the beam. For the bending moment diagram, we know that it varies parabolically. We know that it starts with 0, we know that it ends with 0 on the right hand side of the beam, and we know that we must draw the bending moment diagram underneath. And that means the only shape we can possibly have is the parabola as shown. How do we calculate the value of the maximum bending moment? Well, that will occur in the middle, because it's always a symmetrical problem. If you plug in the value of x equals L upon 2 into the equation we discovered before, you will find that the bending moment in the center of the beam is WL squared upon 8. This is one of the most famous results in structural engineering.